Hello, everyone. I'm Ting Su from East China Normal University. I will introduce our work, benchmarking automated GUI testing for Android against real-world bugs. This work is conducted with Jue Wang from Nanjing University and Zhendong Su from ETH Zurich. As we all know, mobile apps are ubiquitous. Take Android apps as an example. On Google Play, over 3 million apps have been released by many different app companies. However, even those well-known apps like YouTube, Instagram, Facebook may suffer from various quality issues like crashes and incur many user complaints. Thus, ensuring app quality is important. Manual testing or crowdsourced testing is the most widely adopted method to validate app correctness. On the other hand, fully automated GUI testing is another attractive solution. In fact, there have been tremendous continuous progress on improving automated GUI testing in the past decade. For example, at the beginning, Monkey is the only testing tool. Later, Sapiens and Stoat appear and become the well-known baseline technique. And recently, many new testing tools have been developed. However, an overarching question, how effectively and thoroughly can this testing tool find crash bugs in practice, have not been well explored, which requires a ground truth benchmark of real-world bugs. And this is exactly the question our study aims to answer. In fact, before our work, there have been 4 major studies which investigate and understand the effectiveness of existing testing tools. The unique difference between our study and prior ones are, we use real-world bugs as the ground truth, which are reproducible and have non-bug features to benchmark automated GUI testing tool. In this way, we can provide direct and in-depth answers. In addition, we examine tool implementations and discuss with tool authors to validate our findings. Specifically, we constructed such a benchmark and named it as CMIS. CMIS collected 52 critical bugs from 20 open source apps. The reason why we use critical bugs to represent real-world bugs is that we find developers are much more care about critical bugs, which have serious consequences for their users. Thus, we collected critical bugs by mining the issues from GitHub, which are labeled as high priority, blocking release, P1 urgent, etc. And each bug is deterministically reproducible with one GUI level test. In addition to bug dataset, CMIS provides an infrastructure which allows to evaluate any testing tool with one command line. For example, CMIS can specify the device, the buggy app, the testing time, etc. Up to now, CMIS has integrated 8 state-of-the-art tools with different testing techniques. They are Monkey, Ape, Humanoid, ComboJoy, Time Machine, and Q-testing. And we also integrate Stoat and Sapiens, the 2 well-known baseline techniques. To benchmark GUI testing tool, we run each bug per tool for 6 hours and repeat 5 times. The total testing time is over 10,000 CPU hours. And we try to answer 3 research questions. The first research question is, how effectively and thoroughly can this testing tool find the collected real-world bugs? The second question is, are there any common challenges that all these tools face in finding this bug? The third question is, are there any factors affect these tools in finding these bugs? And what are the opportunities for improving the state of the arts? To answer the first research question, we run all these tools on 52 critical bugs, which come from 20 open source apps. And these are the detailed results of all tools of bug finding. Specifically, we find out of 52 bugs, 18 bugs cannot be detected by any tool. We will explain the reasons in the second research questions. Let's take a close look at the detailed bug finding results. By comparing the number of found bugs, we find different tools have different bug finding abilities. And by pairwisely comparing the bugs found by these tools, we find no tools can absolutely outperform the others in finding specific bugs. and we find that individual tools missed a large portion of critical bugs. It indicates existing tools still have a large room for improvement. And by comparing the number of bugs found in all the 5 runs and the number of bugs found in only 1 run, we find existing tools have obvious randomness in finding this bug, and a non-negligible number of bugs were detected by chance. In the second research question, we identified the 5 common challenges faced by all the testing tools by analyzing the 18 bugs that cannot be found by any tool. The first challenge is that existing tools are hard to reach deep usage scenario. For example, 12 out of 18 bugs can only be reached after bypassing more than 5 distinct page transitions. The second challenge is that existing tools do not have careful design of test import generation. We suggest testing tools should also consider corner case, invalid or risky test imports in addition to meaningful ones. The third challenge is that existing tools do not have dedicated consideration of changing system or app settings for finding bugs. The key challenge is that the large search space of GUI tests due to the diverse settings and event interleavings. The fourth challenge is that existing tools are lack of explicit consideration of specific user interaction patterns, which although are very natural user behaviors. We suggest that specific coverage criteria are needed to manifest those bugs that require excising specific sequences of callback interactions. In the third research questions, we investigate the factors that affect testing tools in finding bugs, which are also the opportunities for tool improvement in the future. First, we find GUI exploration strategies indeed affect bug finding. For example, Ape combo droid stored finds more bugs than humanoid Q-testing time machine. One explanation is that Ape combo droid stored more stress tests the control flow and data flow of apps, while the other tools simply steer exploration towards less traveled pages. Thus, we observe that the exploration strategy with more direct and fine-grained guidance seem more effective in finding bugs. Second, we find state abstraction granularity affects bug finding. For example, we find Ape combo droid humanoid uses a fine-grained state abstraction criterion, CLV4, while time machine Q-testing use coarse-grained state abstraction criteria, CLV3, and even between CLV3 and CLV2. It means Ape combo droid humanoid can cover more program states. As a result, Ape combo droid humanoid finds more bugs than time machine and Q-testing. Thus, we observe that the tools with more fine-grained abstraction could detect more bugs, which corroborates the previous findings. However, these findings have not been well recognized by tool developers. Third, we find small heuristic implemented by these tools affect bug finding. For example, only Ape combo droid can do long touch to invoke copy-paste test operation, which can trigger some specific bugs. Although these heuristics are not the fundamental advantages of core testing techniques, they do improve bug finding abilities. Thanks to the CMIS benchmark, we have distilled many interesting findings, most of which are unknown or unclear before. Now we have open source CMIS to benefit the community. We suggest that future tool developers should use CMIS for tool evaluation. Researchers could also use CMIS for other research purposes like program repair and fault localization. We welcome any feedback and contributions for CMIS. Okay, thank you. This is the end of my talk. Thank you for your listening. I would like to take any questions.